Something was pulled from the classified archives of a federal oceanographic database 3 weeks ago, and the people who were supposed to keep it quiet are no longer able to. A research vessel operating in the Central Pacific returned to port with data so anomalous that the lead scientist filed an internal report flagging it for immediate review by agencies that do not typically involve themselves in marine research. That report has now surfaced. Not through a whistleblower in the dramatic Hollywood sense, not through a hack or a data breach, but through the slow, unglamorous machinery of a Freedom of Information Act request filed 18 months ago by an independent marine researcher in Oregon who had noticed something odd in the public-facing sonar charts and decided to pull the thread. What came back to her, after 18 months of delays, redactions, and one outright denial that was later reversed on appeal, was a folder of documents describing an acoustic anomaly in the deep Pacific that does not match any known geological, biological, or man-made source in the scientific literature. And that is where this story begins, because the anomaly is not the discovery. The anomaly is the door. What is behind the door is what made 3 separate government agencies request that the findings be withheld from publication for a period of not less than 5 years. That 5-year classification request was denied, partially. Some of the data came through, enough to understand the shape of what was found, if not every detail of what it means. And the shape of it is something that oceanographers, marine geologists, and deep-sea ecologists are now discussing in terms that range from cautiously extraordinary to quietly terrified. Not terrified in the way that a monster movie manufactures fear from nothing. Terrified in the way that a structural engineer is terrified when they run the load calculations on a bridge that millions of people drive over every day and the numbers come back wrong. It is the terror of a professional confronting data that contradicts the assumptions their entire field was built on. The ocean, which covers 71% of this planet's surface, and which we have explored less thoroughly than the surface of Mars, has apparently been doing something in its deepest layers that our models did not predict, our instruments were not designed to detect at this scale, and our frameworks are not currently equipped to explain. The question of whether it matters for the people living on the surface of this planet is not a rhetorical one. The answer, based on what the documents describe, is yes, significantly. And the timeline attached to that significance is not measured in centuries. Before we go any further, stay with this until the end, because the structure of what happened here, the discovery, the suppression attempt, the partial release, and what the data actually shows, only makes complete sense when you have all of it. The pieces that seem disconnected in the first half of this story are load-bearing walls in the second half, and pulling one out before you understand the others will give you an incomplete picture of something that deserves your full attention. If this is the kind of content that makes you want to stay ahead of what the mainstream conversation isn't having yet, this is the right place for that. Drop a comment right now and tell me where in the world you are watching from, what body of water is closest to you, and whether you have ever thought about what lives and moves and changes in the water beneath the surface you can see. Because after tonight, the way you look at the ocean is going to be different. Now let's get into it. The FOIA request that started this was not filed by a journalist. It was not filed by an activist organization or a political operative looking for ammunition. It was filed by Dr. Mara Elson, an independent marine acoustics researcher who had spent 11 years working for NOAA before leaving to pursue research that she describes in her own published notes as falling outside the institutional comfort zone of federal science agencies. Elson had been analyzing publicly available hydrophone data from the SOSUS network, the sound surveillance system that the United States Navy originally built during the Cold War to track Soviet submarines by listening to the acoustic signatures they produced in the Deep Sound Channel, the SOFAR channel, that layer of the ocean where sound waves travel with extraordinary efficiency over extraordinary distances. The SOFAR channel is one of the most remarkable features of Earth's oceans. It sits at a depth that varies by latitude, but averages somewhere between 600 and 900 meters in most of the Pacific, a depth at which the combination of temperature, pressure, and salinity creates a natural acoustic waveguide. Sound waves entering the channel from above or below bend back toward the channel's center rather than dispersing in all directions, and they travel along it, sometimes for thousands of miles, losing surprisingly little energy along the way. A whale call made near Hawaii can be detected by a hydrophone near Alaska. An underwater earthquake near Japan can be heard by instruments near California. The SOFAR channel is the ocean's nervous system, and SOSUS was built to listen to it. What Elson noticed in the public-facing data was not a single anomalous event. It was a pattern, a subtle but consistent pattern of acoustic returns appearing in a specific frequency range, at a specific depth horizon, recurring at intervals that did not match any known geological process and did not match the behavioral patterns of any known marine species that uses sound in that frequency range. The pattern had been present in the data for at least 4 years. She knew, because she had worked inside the system, that certain portions of the raw SOSUS data are processed and filtered before they reach the public archive. Not all of it is withheld, but the filtering algorithms applied to the raw feed are designed to remove what the processing systems classify as instrument noise, biological interference, and geological background. She also knew, from her years inside NOAA, that those filtering algorithms had been written in the 1990s and updated only twice since then, and that the update criteria were based on the acoustic profiles of known sources. If a source was producing sound in a frequency range that the algorithm had never been trained to recognize as significant, it would be removed from the public data as noise. Elson believed that was exactly what was happening. She filed the FOIA request for the unfiltered raw hydrophone data from a specific section of the Pacific, a roughly triangular area bounded by coordinates she had identified through her own analysis as the likely geographic center of the pattern. 18 months later, partially redacted and accompanied by a cover letter from a NOAA attorney, noting that certain materials had been withheld at the request of 2 other federal agencies whose names were themselves redacted, the data arrived. The unfiltered acoustic record from the target area covers a period of approximately 38 months. Within that period, the data contains something that the filtering algorithm had been systematically removing because it did not match any source in the algorithm's reference library. And the reason it did not match any source in the reference library is straightforward and significant. It is not a source that the reference library was designed to include, because the reference library was built around the assumption that the deep ocean below 4,000 meters in that region was, acoustically speaking, quiet, not silent. The deep ocean is never silent, but quiet in the sense that the sources of sound there are well characterized, geologically stable, and slow-changing. Hydrothermal vent systems produce a consistent, low-frequency hiss. Tectonic microseismicity produces broadband pulses that decay quickly. Biological activity at those depths is sparse and acoustically subtle. What the raw data shows is none of those things. What it shows is a set of acoustic signals originating from depths between 4,200 and 5,800 meters, which is not just deep, it is hadal adjacent. It is the transition zone between the abyssal plain and the upper margins of trench systems. The signals are not continuous. They appear in pulses, irregular in timing but consistent in their spectral character, meaning the frequency composition of each pulse is recognizably similar across the entire 38-month record, as if they are being produced by the same process or the same source or the same type of source repeating. The frequency range itself is part of what makes the signals anomalous. They peak in a band centered around 52 Hz. If that number means anything to you, it should, because 52 Hz is the frequency associated with one of the most famous and most debated acoustic mysteries in ocean science. The so-called 52 Hz whale, first detected in 1989 by the same Navy hydrophone network that Elson was analyzing. The 52 Hz whale, which called at a frequency higher than any known baleen whale species and has never been visually confirmed, became a cultural phenomenon, described in popular media as the loneliest whale in the ocean, calling in a frequency no other whale could hear. But the signals in Elson's data are not whale calls. They do not have the temporal structure of biological vocalizations. They do not modulate in the ways that marine mammal sounds modulate. They are more structured than biology tends to produce, but less structured than any known anthropogenic source. They sit in an uncanny acoustic valley between the organic and the mechanical, and the scientists who have now reviewed the data independently are careful and deliberate in saying they do not know what is producing them. That careful deliberateness is itself a signal, because these are not people who are easily impressed by unusual data. These are researchers who have spent careers in the deep ocean and who have encountered many things that initially seemed inexplicable and turned out, on closer examination, to have mundane explanations. They are being careful because on closer examination, this one is not becoming more mundane. It is becoming more strange. Let's talk about what 4,200 to 5,800 meters actually means, because the number deserves more than a passing reference. The average depth of the world's oceans is approximately 3,688 meters. That average is pulled upward by the vast, shallow continental shelves and pulled downward by the deep trenches, and the middle of that range, the abyssal plain, is where most of the ocean floor sits. At 4,200 meters, you are on the abyssal plain. You are in a world of near absolute darkness, where the pressure is approximately 420 atmospheres, which means every square inch of a structure at that depth is bearing a force of roughly 6,000 pounds. The temperature is between 2 and 4 degrees Celsius. The water is extraordinarily still, not calm in the surface ocean sense of a flat sea on a quiet day, but still in a deeper physical sense. Convective mixing, which drives so much of what happens in the upper ocean, essentially ceases at these depths. The deep ocean is stratified in ways that the surface ocean is not, and that stratification is one of the reasons that what happens in the deep ocean tends to stay in the deep ocean, isolated from the processes that govern what we see and measure at the surface. At 5,800 meters, you are approaching the upper margins of the Hadal Zone, the deepest 6% of the ocean by volume, but representing something categorically different from the abyss above it. The Hadal Zone is defined by the trenches, the linear scars in the ocean floor produced where tectonic plates converge and one slides beneath the other. The Mariana Trench reaches to nearly 11,000 meters. The Tonga Trench exceeds 10,000. The Philippine Trench, the Kermadec, the Kuril-Kamchatka. These are not just deep places. They are windows into a different physical regime entirely. The reason the source depth matters is this. The acoustic signals Elson identified are not coming from a known geological feature. The bathymetric charts of the target area, the maps of the seafloor's depth and topography, show an area of abyssal plain that is geologically unremarkable on its face. There are no mapped hydrothermal vent fields at those coordinates. There are no known fault systems that would produce the kind of recurrent acoustic activity described in the data. There are no seamounts, no submarine volcanic features, no structural elements of the seafloor that would provide an obvious physical mechanism for producing consistent, spectrally stable acoustic pulses over a period of 38 months. The document that accompanied the released data includes a single-paragraph note from what appears, based on redaction patterns, to be a geophysicist attached to one of the withholding agencies. The note says, and this is a direct quote from the released document, "The source characteristics are inconsistent with known geological processes in the survey area and warrant ground truth investigation before further distribution of findings." That language, warranting ground truth investigation before further distribution of findings, is the bureaucratic equivalent of a fire alarm. It means, we do not know what this is, and we are not ready for the public conversation about it. Before this story goes where it is going to go, it is worth spending serious time on the biological dimension, because the biology of the deep ocean is not a side note to this story. It is one of its central and most consequential threads. The deep ocean is, by any reasonable measure, the least explored biome on Earth. We have surveyed less than 25% of the global seafloor with any precision, and the surveys we have conducted have been concentrated along routes that are scientifically or economically motivated. Mid-ocean ridges because of their geological significance, continental margins because of their hydrocarbon potential, and a handful of trench systems because of their extreme environments and the organisms adapted to them. The vast stretches of abyssal plain that cover most of the ocean floor have received only scattered sampling, and what those samples have returned has repeatedly revised upward the scientific community's estimates of how many species live in the deep ocean and how complex the communities of life there actually are. In 1977, the discovery of hydrothermal vent ecosystems at the Galapagos Rift transformed biology. Here were entire communities of organisms, from giant tube worms to chemosynthetic bacteria to unique species of crabs and fish and mollusks, living without any dependence on sunlight, running entirely on chemical energy from the Earth's interior. Before 1977, the prevailing assumption was that the deep ocean was a biological desert, sparsely populated by organisms that subsisted on the thin rain of organic material sinking from the sunlit upper ocean. After 1977, that assumption was gone, replaced by the understanding that the deep ocean contains its own energy sources and its own trophic systems independent of the sun. Since 1977, each major expedition to the deep has returned findings that extend that revision further. Cold seep communities, which form around areas where hydrocarbon-rich fluids and methane bubble up from the seafloor, are now known to occur across all ocean basins and to support diverse and productive ecosystems. Whale falls, the bodies of dead whales that sink to the seafloor, are now understood to support a succession of biological communities over periods of decades, functioning as biological stepping stones that allow species to move between the isolated islands of productivity that vent and seep communities represent. The Hadal Zone, once thought to be nearly sterile due to the combination of extreme pressure, low temperature, and near-total dependence on material sinking from thousands of meters above, has been found to host unique amphipod communities of astonishing abundance, specialized fish species that have adapted to pressures that would crush any unspecialized vertebrate, and bacterial mats of undetermined diversity. The deep ocean is not empty, it is full, and we have only begun to understand the nature of that fullness. This matters for Elson's data because one of the first and most obvious questions any scientist asks when confronted with an unexplained acoustic signal in the ocean is, could this be biological? And the answer to that question, in this case, has been examined carefully and returned as possibly, but not in any way we currently understand. If you are watching this and you have stayed with it this far, you are the kind of person this channel exists for. The ocean is the least understood system on this planet, and the most consequential, and the story we are building right now is not going to appear on the front page of tomorrow's newspaper. It is being assembled in the margins of federal documents and the careful language of scientists who are choosing their words with the precision of people who know exactly what they are and are not willing to claim. If that kind of careful, evidence-based assembly of genuinely strange and genuinely important information is what you come here for, this channel is built on exactly that. Subscribe if you haven't yet, because the next part of this story is where the biology and the acoustics and the geological data start to converge, and where the classification request starts to make a different kind of sense than it did at the beginning. Running parallel to the acoustic investigation and only connected to it after the FOIA documents were released is a second data stream that has received almost no public attention despite being derived from instruments that are entirely public, maintained by an international consortium, and accessible to any researcher with the patience to query the database. The Argo Float Network is one of the most ambitious oceanographic monitoring programs in history. It consists of approximately 4,000 autonomous floats distributed across the global ocean, each one programmed to sink to a depth of 2,000 meters, drift with the deep currents for 10 days, then rise to the surface while taking continuous measurements of temperature and salinity through the water column, transmit its data via satellite, and then sink again to repeat the cycle. The Argo network has been operational since the early 2000s and has provided an unprecedented continuous record of the ocean's interior thermal structure. It is the closest thing oceanography has to a global nervous system, and its data is open, public, and updated in near real time. What several researchers, working independently and without knowledge of Elson's investigation, noticed in the Argo data from the same geographic region as the acoustic anomaly is a thermal signature in the deep water column that does not fit the expected seasonal or interannual variability patterns for that area. Specifically, there are floats in the target region that have been recording temperature values in the 800 to 1,500 meter depth range that are consistently, persistently, and statistically significantly warmer than the climatological baseline for those depths at that location and in those seasons. The warming is not large in absolute terms. We are talking about anomalies in the range of 0.2 to 0.4 degrees Celsius above the long-term average. That sounds trivial. It is not trivial. The deep ocean is thermally stable to a degree that the surface ocean is not. The processes that drive temperature variability in the upper ocean, solar heating, evaporative cooling, wind-driven mixing, surface current variability, all of these decay with depth. By 800 meters, the ocean has become genuinely cold and genuinely stable. Year-to-year temperature variability at that depth in that region under normal conditions is measured in hundredths of degrees, not tenths. A persistent anomaly of 0.2 to 0.4 degrees at that depth is not background noise. It is a signal. And when you map it geographically, the warmer than expected water forms a rough column. It is not spread uniformly across the region. It is concentrated in an area that, when you overlay the bathymetric charts, sits directly above the section of abyssal plain from which the acoustic signals are originating. A thermal anomaly in the water column above an acoustic anomaly from the seafloor below, both in the same geographic area, both persistent over a multi-year period, both falling outside the established ranges of known processes. The probability of that being coincidence is not zero, but it is not large, and the researchers who have looked at both data sets simultaneously are not treating it as coincidence. Here is the question that the biology of the deep ocean forces onto the table, and it is a question that the scientific community has been circling carefully without landing on it directly. Is it possible that the acoustic signals and potentially the thermal anomaly are associated with biological activity of a scale and type that has not previously been documented in that region or at those depths? The careful answer is yes, it is possible. And the reason it is possible is rooted in what deep-sea expeditions have found with remarkable consistency. The deep ocean surprises us every time we go there with serious instruments. The 2022 Schmidt Ocean Institute expedition to the Ningaloo Canyon off Western Australia returned with footage of a siphonophore, a colonial organism related to the Portuguese man-of-war, estimated to be 45 to 47 meters in length. That is longer than a Boeing 747. It is the largest organism ever recorded. It was living in water nobody had looked at carefully before, in a canyon that appears on charts as an unremarkable feature of the continental margin, doing whatever siphonophores do at depth, while the surface world went about its business, completely unaware of its existence. The giant squid, Architeuthis dux, which can reach lengths of 13 meters and is the largest invertebrate known to science, was never photographed alive in its natural habitat until 2004. Before that, everything we knew about it came from dead specimens, including the partially digested remains found in the stomachs of sperm whales, which told us that something big enough to fight sperm whales was living in the deep ocean, but that we had never once seen it alive. We had been sailing over it and trawling through the water above it and theorizing about it for a century, and we had never seen it alive. The mesopelagic zone, that twilight layer between roughly 200 and 1,000 meters depth, is home to what may be the largest daily migration of biomass on Earth. Every night, enormous numbers of small fish, crustaceans, and gelatinous organisms migrate upward toward the surface to feed in the productive sunlit layer, then descend again before dawn to hide from visual predators in the darkness. This migration, called the Deal vertical migration, involves a total biomass that some estimates place at between 1 and 10 billion tons, moving up and down through the water column every single day. The range of that estimate, a factor of 10, tells you how uncertain we are about the scale of something happening in our own ocean every night. Against that backdrop of documented ignorance about organisms and communities we know exist, the question of what might be producing large-scale, spectrally consistent acoustic signals from the deep abyssal plain is genuinely open. Not open in the sense of being without constraint. There are things that physics and biology tell us cannot be responsible, but open in the sense that the category of possible explanations includes things that would require fundamental revision of our understanding of what kinds of organisms exist at those depths and what they are capable of doing. And that revision, if it comes, would not be the first time the deep ocean has forced us to rewrite a chapter we thought was finished. There is a third possible explanation for what the data shows, one that sits between the biological and the anthropogenic categories, and one that has a different, and in some ways more immediately concerning set of implications. The target area of the Pacific sits within a region of the seafloor that has been geologically active over millions of years in ways that are not obvious from the surface topography. Beneath the relatively flat abyssal plain, the oceanic crust is not uniform. It is layered, fractured by the stresses of plate movement and cooling, and in some areas underlain by magmatic systems that are technically extinct, but that retain residual heat in their surrounding rock for timescales of millions of years. In certain configurations, these residual thermal systems can interact with the deep circulation of seawater through the porous upper layers of the crust in ways that produce low-temperature diffuse fluid flow, chemical exchanges between seawater and rock, and, under the right conditions, acoustic emissions as fractures propagate through thermally stressed rock or as fluid movement through fracture networks generates what seismologists call tremor, a sustained quasi-continuous seismic signal quite different from the sharp impulsive signals produced by discrete earthquake events. Tremor has been documented at subduction zones, at mid-ocean ridges, and associated with volcanic systems, but it has not been documented at the coordinates of Elson's target area, and the spectral characteristics of the acoustic signals she identified do not match the known signatures of tectonic or volcanic tremor. However, and this is an important qualification, what has not been documented and what does not exist are not the same thing, especially in a region of the ocean that has not been the subject of dedicated geophysical study. There is a more specific and more alarming geological hypothesis that has been raised in the technical discussions now circulating among the researchers who have seen the data. The target area sits in a part of the Pacific where the seafloor sediment column contains what are called gas hydrate deposits, sometimes called methane clathrates. These are crystalline structures in which methane molecules are trapped inside cages of water ice at the low temperatures and high pressures of the deep sea floor. Gas hydrates are stable under specific conditions of temperature and pressure, and they are extraordinarily widespread. The global inventory of carbon stored in seafloor methane hydrates is estimated to be roughly twice the total carbon in all other fossil fuel reserves combined. They are, in the language of Earth system science, a sleeping giant. The reason the word sleeping is used carefully is that hydrate stability is sensitive to temperature. When the temperature of the deep water above a hydrate deposit rises, or when the pressure decreases due to sea level change, the hydrates can begin to destabilize. As they do, the methane they contain is released, bubbling upward through the sediment and into the water column and eventually into the atmosphere. Methane is a greenhouse gas approximately 80 times more potent than carbon dioxide over a 20-year timescale. A large-scale destabilization of seafloor methane hydrates would represent a climate feedback of potentially catastrophic speed and scale, one that could in principle accelerate warming in ways that no policy or technology currently deployed or under development could intercept. The acoustic signals from the target area are consistent in some of their characteristics with the sound of methane bubbling through water-saturated sediment. They are not conclusive evidence of hydrate destabilization, but they are not inconsistent with it, and the thermal anomaly in the water column above the source region adds a layer of concern that the researchers involved are choosing, carefully, not to dismiss. 20 minutes into this, and I want to pause because this is the moment in a story like this where the weight of what we're assembling starts to feel like a lot to carry. The acoustic anomaly, the thermal signal, the geological wildcard, the partial classification, the 18-month delay before the data appeared. These are not independent curiosities. They are threads in the same fabric, and the fabric is beginning to show its pattern. If this kind of deep, evidence-based investigation into what the ocean is doing below the surface is what you want more of, this channel is committed to exactly this. Subscribe and stay with the story, because the next section is where we talk about what happened when independent researchers tried to mount an expedition to the target area and why that expedition was not straightforward. Within 6 weeks of Elson publicly releasing her analysis of the FOIA data, which she did through a combination of a preprint posted to the Earth and Space Science Open Archive and a long-form piece published in an independent marine science newsletter with a readership of roughly 12,000 oceanographers, marine biologists, and science journalists. 3 separate groups had contacted her expressing interest in organizing a ground truth expedition to the target area. Ground truth is the operational term for going to the place the data says is interesting with real instruments and finding out whether what the data suggests is actually there. It is the most important step in any scientific investigation that has, to that point, been conducted entirely through remote sensing, and it is the step that the federal document had explicitly called for before further distribution of findings. The most serious of the 3 groups was a consortium assembled by a Marine Research Foundation operating out of Honolulu, with access to a research vessel rated for deep water operations and a suite of instruments including multi-beam sonar systems capable of mapping the seafloor at high resolution, a towed hydrophone array for acoustic characterization, a deep-rated autonomous underwater vehicle capable of reaching 6,000 meters, and an ocean bottom seismometer package that could be deployed to the seafloor to record acoustic signals from within the medium rather than from above it. This was not a hobbyist operation. This was a serious scientific expedition with serious equipment and serious people behind it. The expedition application was filed with NOAA's Office of Ocean Exploration and Research, which coordinates the allocation of research vessel time and provides permitting for certain categories of deepwater research in international waters. The application was straightforward. The target area is in international waters, well beyond any nation's exclusive economic zone, and research in such areas does not typically require anything more than standard safety and environmental compliance documentation. The application was received, an acknowledgement was issued, and then, for 11 weeks, nothing happened. When the consortium's principal investigator followed up, she was told that the application was under review by an interagency working group that had been convened to evaluate research activities in the target region. This was unusual. Interagency working groups do not typically convene to review routine oceanographic expedition applications. When the PI asked which agencies were represented on the working group, the NOAA representative she spoke with said she was not able to share that information. When she asked what the timeline for the review was, she was told the working group would complete its review in a timely manner. The expedition was eventually approved after a total delay of approximately 5 months, with 2 conditions attached that had never previously appeared in any expedition approval the PI had received in 18 years of leading deepwater research. The first condition was that all raw data collected during the expedition must be shared with NOAA within 48 hours of collection. The second condition was that preliminary findings must not be publicly released until they had been reviewed by the interagency working group for a period not to exceed 90 days. The PI accepted the conditions. The expedition sailed. The autonomous underwater vehicle deployed from the research vessel during the first operational day of the expedition descended through 4,000 meters of water column over a period of several hours, following a programmed survey track designed to cover the geographic area identified in Elson's acoustic analysis while collecting video, sonar, and water column chemistry data. The AUV is not capable of real-time communication at depth. Its data is stored internally and downloaded when it surfaces. The first dive lasted 18 hours. When the vehicle surfaced and the data was downloaded, the lead scientist on the expedition described the initial review of the imagery as, in her words, one of the most disorienting experiences of my professional life. The seafloor in the target area is not what the bathymetric charts suggested it should be. The charts, compiled from surface ship sonar surveys of varying vintage and resolution, showed a relatively featureless abyssal plain with gentle topographic relief. The AUV imagery showed something different. The seafloor in the core of the target area is actively venting. Not from a discrete hydrothermal vent structure of the kind associated with mid-ocean ridges, with their chimneys and their superheated mineral-laden fluids, but diffusely across an area of seafloor estimated from the AUV's track and sensors to encompass at least several square kilometers, possibly significantly more. The venting is low-temperature fluid flow, seeping through the sediment rather than erupting from a geological structure, and the sediment around the venting areas shows visual evidence of disruption. Areas where the normal fine-grained sediment blanket has been displaced, pockmarks of varying sizes that are consistent with episodic methane venting events, and at least 2 locations where the AUV's cameras recorded what appear to be active bubble streams rising from the sediment surface. The bubble streams are the detail that changed the tone of the expedition. Methane bubbles in the deep ocean do not always reach the surface. At depth, the high pressure and low temperature cause methane to dissolve into the surrounding water rather than remaining in the gas phase, and the bubbles shrink and disappear as they rise through the water column. But the fact of their existence at the seafloor is significant regardless of what happens to them on the way up, because active bubble venting at the seafloor is evidence that the subsurface hydrate or free gas reservoir is under sufficient pressure to be releasing material into the water column. It means the system is dynamic, not static. It means that something has changed, or is changing, in the conditions that had previously kept the subsurface gas contained. And it means that the acoustic signals Elson detected may have a source that is neither purely geological nor purely biological, but is, in the most literal sense, the sound of the seafloor exhaling. The water column chemistry data collected by the AUV on that first dive confirmed elevated methane concentrations in the bottom water directly above the venting areas, concentrations significantly above background levels for the region. By the time the expedition team was processing the data from the first dive and planning the second, the 90-day review condition attached to their expedition approval had taken on a different weight than it had when they signed the agreement. They now had data they believed the public needed to understand, and they had agreed not to release it for 3 months. Let's step back from the sequence of events and spend serious time on what a diffuse methane venting field of the apparent scale and activity level described in the expedition data actually means in the context of ocean science and climate science, because this is where the story stops being primarily about a mysterious acoustic signal and becomes something larger and more consequential. The world's oceans have absorbed approximately 25% of all the carbon dioxide emitted by human industrial activity since the beginning of the industrial era. They have also absorbed more than 90% of the excess heat generated by the enhanced greenhouse effect. This is a remarkable and in some ways fortunate fact. Without the ocean's capacity to act as a carbon and heat sink, atmospheric concentrations of CO2 would be significantly higher than they are, and surface temperatures would have risen faster and further than they have. But the ocean's role as a carbon sink is not infinite, and it is not stable. It is dynamic, and it is sensitive, and it operates through processes that interact with each other in ways that are not always linear and not always predictable.
The fresh basalt indicates
The methane hydrate system of the deep ocean is one of those interactive, non-linear processes. Hydrates store methane, and they are stable under cold, high-pressure conditions. If the deep ocean warms, even slightly and slowly, the stability field of hydrates shifts. Hydrates that were stable at the boundary of their stability envelope become unstable. The methane they contain is released. That methane enters the water column, and some fraction of it, depending on the depth and the rate of release, reaches the atmosphere. In the atmosphere, methane enhances the greenhouse effect, contributing to further warming, which further warms the ocean, which further destabilizes hydrates. This is a feedback loop, not a hypothetical one constructed by climate modelers in a scenario exercise, but a real physical process that is documented in the geological record of past climate changes, and that is an active subject of concern in the current literature on climate tipping points. The critical question, and it is a question that the expedition data begins to address but does not yet answer, is how large is the venting field in the target area, and what is the rate of methane release from it? Scale and rate are everything in this analysis. A small venting field releasing methane slowly into a deep water column, where most of it dissolves before reaching the atmosphere, is a scientific curiosity and a local biogeochemical feature, not a global climate signal. A large venting field releasing methane rapidly, or releasing it at depths shallow enough that significant fractions reach the atmosphere, or acting as one of many simultaneous venting areas across a broader region is a different thing entirely. The expedition team conducted only 2 AUV dives before the vessel's scheduled departure. Those 2 dives covered a fraction of the total area that the acoustic data suggests is anomalous. The full extent of the venting field is unknown. The rate of methane release has been estimated from the water column chemistry data, but with large uncertainty bounds. What is known is that the field exists, that it is active, and that it is located in a region where it was not expected and where the available monitoring infrastructure was not designed to detect it. That last point, the monitoring infrastructure point, is not a small one. If this venting field exists in the Central Pacific without anyone having detected it until an independent researcher noticed something odd in acoustic data that the standard filtering algorithms were removing as noise, then the question of how many similar features exist in the vast, unmonitored stretches of the deep ocean is not a rhetorical one. It is a measurement problem of enormous practical importance. 40 minutes into this, and the architecture of the story has now fully assembled itself. The acoustic signal, the thermal anomaly, the expedition, the methane venting field. These are not separate incidents. They are one thing, seen from different angles with different instruments. And the implications of that one thing extend beyond oceanography into every system that depends on the ocean's stability, which is every system on this planet. This channel exists to go where the mainstream conversation isn't going yet, to the actual data, the actual documents, the actual science, and to bring it to you in a form that respects your intelligence and your time. If you are not subscribed, now is a genuinely important moment to do that. Because what comes in the next section, the part about why the classification request was made and what the agencies involved were apparently concerned about, is the part that connects all of this to the world above the waterline. The question of why 2 federal agencies requested a 5-year classification period for data describing an ocean floor venting field has several possible answers, and they are not mutually exclusive. The first and most charitable is that the agencies involved were exercising caution in a situation where the data was preliminary. The implications were potentially alarming, and the risk of premature public communication triggering unnecessary concern was assessed as outweighing the risk of delayed disclosure. This is a real and legitimate concern in science communication. Preliminary findings do get misinterpreted. Partial data does get extrapolated beyond what it supports. The history of environmental science communication includes examples of early reports that were technically accurate but presented in ways that created more alarm than was warranted by the evidence at that stage, and the correction of those over-communications, when it came, did damage to public trust in the underlying science. An agency worried about that dynamic might reasonably request a review period before public release. The second possibility, less charitable but also grounded in historical precedent, is that the findings had economic implications that certain interests would prefer to delay acknowledging. The target area of the Pacific overlaps with a region where seafloor mineral extraction rights have been applied for by several entities under the framework administered by the International Seabed Authority. Polymetallic nodule fields on the abyssal plain in that part of the Pacific contain commercially significant concentrations of manganese, cobalt, nickel, and copper, and the deep-sea mining industry has been actively pursuing the right to extract them. A discovery that the seafloor in the target area is an active methane venting field would have direct implications for the environmental assessment of proposed mining activities there. because disrupting the seafloor sediment in a methane venting area carries different risks than disrupting it on a geologically quiescent abyssal plain. The third possible reason for the classification request is the one that the researchers involved are most reluctant to articulate publicly, but that surfaces in careful conversations and in the subtext of the technical documents. The data, if it represents what it appears to represent, has implications for existing climate models and for the policy frameworks built on those models that the agencies involved may not have been prepared to manage publicly. If the venting field in the target area is part of a broader pattern of hydrate destabilization in the Pacific that has not been captured by existing monitoring systems, then the carbon budget projections and climate trajectory models that inform international climate agreements, emissions reduction targets, and adaptation planning may be missing a significant term. Not a small correction, not a rounding error, but a term that could alter the timeline and magnitude of projected warming in ways that policy frameworks are not currently designed to incorporate. Acknowledging that possibility publicly, before the data is fully characterized and the modeling implications are worked through, would create a scientific and political problem of considerable complexity. The agencies involved in the classification request may have been buying time to understand what they were dealing with before anyone was asked to respond to it. Whether that time buying serves the public interest or undermines it is a question that reasonable people can disagree on. But the public's interest in knowing that the deep ocean is doing something our models did not predict, something that may have consequences for the trajectory of a warming planet, is not a question with an ambiguous answer. The public interest in that information is clear, and it is significant. The story of what was found in the Central Pacific is partly a story about a specific discovery, and partly a story about a system of observation that was never built to find it. Understanding both is necessary to understanding what the discovery means and what the appropriate response to it looks like. The global ocean monitoring infrastructure, comprehensive as it has become relative to what existed 50 years ago, was designed around a set of assumptions about where the interesting things were happening and where the risks were located. The Argo Float Network monitors temperature and salinity throughout the upper 2,000 meters of the ocean globally, but its sensors are not designed to detect methane, and its floats do not go below 2,000 meters, which means the lower half of the ocean by depth. Below 2,000 meters, where the abyssal and hadal environments are, is not covered by the network's primary measurement capability. The hydrophone networks maintained by various nations, including the SOSUS array and its more recent equivalents, are powerful acoustic monitoring tools, but their data is processed through filtering algorithms designed around known source categories. And as Elson's investigation demonstrated, novel sources that fall outside the reference library can be systematically removed from the public data stream as noise. Satellite-based ocean monitoring, which provides extraordinary coverage of the surface ocean through measurements of sea surface temperature, ocean color, surface height, and wind speed, has no ability to see below the surface at all. The surface of the ocean is the most monitored part. The deepest parts are the least monitored, and the relationship between those two facts and our understanding of the ocean as a system is not comfortable. The deep sea research community has been making the case for improved deep ocean monitoring for decades, and the case has been heard but not fully funded. The comprehensive deep ocean observation system that scientists argue is necessary to understand what is happening in the abyssal and hadal zones and to detect changes in those zones with the timeliness that would make the information actionable would require a fundamentally different level of investment than has been politically achievable in any country with significant ocean science capacity. The instruments exist. The scientific understanding to design the system exists. The data management infrastructure to handle the data streams it would generate is increasingly available. What has not materialized is the political will to treat the deep ocean as a monitoring priority on the same level as the atmosphere or the upper ocean, despite the fact that the deep ocean contains more heat, more carbon, more uncharacterized biology, and more potential for consequential surprises than the parts of the ocean we do monitor well. The discovery in the Central Pacific, if it represents what the preliminary data suggests, is an argument for that investment that is more concrete and more urgent than anything previously available. It is evidence, not theoretical argument, that the deep ocean is capable of presenting surprises of climate relevance in places we were not looking and at scales we were not prepared to detect. The cost of not knowing what the deep ocean is doing has, in this case, been a 5-year classification request, an 18-month FOIA delay, and a discovery that emerged from the data through the persistence of a single independent researcher working outside the institutional framework that should have found it first. The academic response to Elson's preprint and the Expedition Consortium's preliminary report, which was released in summary form after the 90-day review period expired with no response from the interagency working group, has been careful, measured, and in its carefulness, revealing. Peer reviewers and public commentators in the field have not dismissed the findings. They have not claimed the data is fabricated or the analysis is flawed. What they have done, almost universally, is call for more data, larger surveys, longer time series, and independent replication. This is the normal scientific response to preliminary findings of significant consequence, and it is the right response. It is also, and this is the revealing part, a response that implicitly accepts the premise that the findings are worth taking seriously enough to warrant the investment that more data, larger surveys, and independent replication would require. Scientists do not call for extensive follow-up work on findings they consider obviously wrong or trivially explained. The calls for follow-up are the scientific community's way of saying, "We do not know how to dismiss this, and we are not comfortable doing so, and we believe it is important enough to investigate properly." Dr. James Whitmore, a marine geochemist at the University of Southampton who has published extensively on methane hydrate dynamics, wrote in a commentary accompanying the preprint that the combination of acoustic anomaly, water column thermal signature, and direct visual evidence of seafloor venting, if confirmed by further investigation, would represent the largest undocumented seep field in the Pacific and would necessitate a significant revision of regional carbon flux models. The phrase "necessitate a significant revision of regional carbon flux models" in the dry language of academic science is the equivalent of saying, "This changes something important." Dr. Yuki Tanaka, a deep-sea biologist at the Japan Agency for Marine Earth Science and Technology, wrote a separate commentary focused on the biological implications, noting that a diffuse venting field of the apparent scale described in the expedition report would be expected to support chemosynthetic biological communities that have not been characterized, and that the acoustic signals, while not consistent with any known organism, were worth considering in the context of what is not yet known about acoustic behavior in deep chemosynthetic ecosystems. That sentence, worth considering in the context of what is not yet known, carries significant weight coming from a scientist at JAMSTEC, an institution that has conducted more deep-sea expeditions than almost any other organization on Earth. It is not a scientist claiming to know what the source of the acoustic signals is. It is a scientist refusing to rule out an explanation that their training and experience tells them cannot be excluded, even though it would require the existence of something that has not previously been documented. The conversation in the scientific community is not settled. It is open, it is serious, and it is moving in a direction that suggests the target area of the Central Pacific is going to receive significantly more attention from significantly better equipped expeditions in the coming years. The findings are being taken seriously by people who have every professional incentive to dismiss extraordinary claims, and they are not dismissing them. 1 hour into this story, and if you are still here, you have done something that most people scrolling past headlines never do. You have stayed with a complicated, layered, genuinely important story long enough for its full shape to become visible. The acoustic anomaly, the thermal signal, the expedition, the venting field, the classification attempt, the monitoring gap, the scientific response. These are not separate items in a list. They are parts of a single picture, and the picture is of an ocean doing things we did not know it was doing in places we were not looking, with implications that extend from the seafloor to the atmosphere to the policy frameworks that govern our response to a warming planet. This channel will stay on this story. Subscribe if you want to be here when the next piece of data lands, because it is coming. At this point in the story, intellectual honesty requires doing exactly what was done earlier in the analysis, stepping back and asking whether the pattern we are seeing is as significant as it appears, or whether our pattern-detecting brains are assembling a compelling narrative from pieces that are real, but whose connections are less certain than the narrative suggests. This is not a rhetorical move to deflate the story. It is the most important discipline in evidence-based science communication, and the failure to apply it is what distinguishes serious analysis from sensationalism. Let's be precise about what is established and what is inferred. What is established? An acoustic anomaly exists in the target area, confirmed by multiple independent analyses of the raw hydrophone data. A thermal anomaly exists in the water column above the target area, documented in the Argo float record. Seafloor venting, including visual evidence of bubble streams, was recorded by the expedition AUV. Elevated methane concentrations were measured in the bottom water above the venting area. What is inferred but not yet established? The venting field extends over a large area, larger than the AUV survey covered. The methane flux from the field is significant relative to the regional carbon budget. The venting is linked to hydrate destabilization rather than other possible geological sources, such as thermogenic gas migration from sedimentary basins. The acoustic signals are produced by the venting activity rather than by some other source. The thermal anomaly is caused by the venting rather than by large-scale ocean circulation variability. And critically, none of these caveats diminish the significance of what is established. They define the boundary between what the evidence currently supports and what further investigation might confirm or refute. The appropriate response to this situation is neither to claim the established findings prove everything the inference chain suggests, nor to dismiss the established findings because the inference chain is incomplete. It is to treat the established findings as exactly what they are: a compelling set of observations that warrant serious, well-resourced scientific investigation that have already prompted a classification request suggesting that someone with institutional authority believed the implications were significant enough to require management, and that have produced a response from the scientific community consistent with findings considered important and credible. The ocean is large, and our knowledge of it is incomplete. The incompleteness of our knowledge cuts in two directions. It means we should be humble about our ability to interpret anomalous findings that fall outside established frameworks. But it also means we should be humble about our tendency to assume that if something large and significant were happening in the deep ocean, we would already know about it. The history of ocean science is a history of being surprised by the size, the diversity, and the dynamism of a system we access only with difficulty and sample only sparsely. The story of the Central Pacific acoustic anomaly and the expedition that followed it is, at its core, a story about that gap between what we assume we know and what the ocean actually contains. Whether the specific implications, the venting field, the methane, the possible climate signal, are as significant as the preliminary data suggests is a question that more and better science will answer. But the question itself, the fact that such a question can be legitimately posed on the basis of real data from the actual ocean, is significant in its own right, and it is the reason this story matters. The ocean below 200 meters, everything below the sunlit productive zone that drives the biological and chemical dynamics most people picture when they think of the sea, is connected to the surface world through a set of physical and chemical pathways that are slower than the processes at the surface, but that are, over the timescales relevant to climate, enormously consequential. The ocean's deep circulation, the thermohaline conveyor belt that moves water from the surface to the deep and back over periods of hundreds to thousands of years, is the mechanism by which the deep ocean absorbs and stores the heat and carbon that the surface takes up from the atmosphere. It is the reason the ocean's enormous heat and carbon capacity is accessible to the global climate system rather than locked at depth with no connection to the surface. It is also the reason that changes in the deep ocean, even changes that are occurring slowly by human standards, can eventually propagate back to the surface and to the atmosphere in ways that alter the global energy balance. The methane hydrate system sits at the interface of this dynamic. Hydrates form when deep cold water bathed in dissolved methane maintains conditions within the hydrate stability field. They dissolve when those conditions change. The conditions that determine their stability, bottom water temperature, and the pressure of the overlying water column are themselves determined partly by the thermohaline circulation and partly by the total heat content of the ocean. As the ocean accumulates heat from the enhanced greenhouse effect, the question of whether and when that heat reaches the depths where hydrates are stable is one of the most important and most uncertain questions in climate science. The finding in the Central Pacific, a venting field at depths where hydrates should be stable under baseline conditions, suggests that either the baseline conditions in that location are not what we assumed, or that conditions have changed enough to push a local hydrate system outside its stability field. The connection between the deep ocean and the surface world is not just physical and chemical. It is increasingly economic and political as the deep seafloor becomes a target for mineral extraction, cable laying, and other industrial activities that have historically been concentrated in shallower coastal waters. The deep-sea mining industry, which seeks to extract polymetallic nodules, cobalt-rich crusts, and seafloor massive sulfide deposits from the abyssal plain and seamount environments, operates in a regulatory framework that is still being developed and that is, by most assessments, significantly behind the pace of the industry's ambitions. The environmental assessments conducted to evaluate proposed mining activities rely on baseline characterizations of the areas to be mined, and those baseline characterizations are only as good as the surveys on which they are based. If a significant proportion of the deep Pacific seafloor contains active methane venting features that have not been detected by existing surveys because the monitoring infrastructure was not designed to find them, then the baseline assessment supporting mining approvals in those areas may be fundamentally incomplete. The regulatory framework governing deep-sea mining cannot protect features it does not know exist. The discovery in the Central Pacific and the monitoring gap it exposed are relevant not just to climate science and ocean science, but to every framework that makes decisions about the deep ocean on the basis of assumptions about what is there. Those assumptions may need revision, and the revision may be significant, and the scale of the ignorance that the discovery revealed is itself one of the most important findings to emerge from the whole sequence of events. The 90-day review period attached to the expedition's data sharing agreement expired without a formal response from the interagency working group, which the expedition's principal investigator interpreted as constructive permission to release the summary findings, which she did through the same independent science communication channels that Elson had used for her initial analysis. The full data set, under the terms of the expedition agreement, remains with NOAA pending the completion of whatever review process is underway. A follow-up expedition is being planned by the same consortium, this time with a larger vessel, additional AUV capacity, ocean bottom seismometers for permanent deployment at the site, and a commitment from 3 university oceanography departments to contribute scientific personnel and analytical resources. Funding applications are pending at 2 private foundations and 1 national science agency. The timeline for the follow-up expedition, if funding is secured, is approximately 14 to 18 months from the date of Elson's original preprint, which means the expedition could be at sea by mid to late next year. In the meantime, Elson and several collaborators are conducting a systematic reanalysis of the broader hydrophone dataset from the Pacific, looking for acoustic signatures similar to those in the target area at other locations. The reanalysis is being conducted on the unfiltered raw data that the FOIA process returned, and preliminary results, which Elson has shared informally with colleagues but not yet published, suggest that the target area may not be unique. There may be other locations in the Pacific exhibiting similar acoustic characteristics, currently being removed from the public data record by the same filtering algorithms that hid the original signal. If that preliminary finding is confirmed by the full reanalysis, the implications expand considerably. A single unexpected venting field in a remote part of the Pacific is significant. A pattern of such features distributed across the Pacific abyssal plain, all currently invisible to the standard monitoring infrastructure, would be a different kind of finding with a different order of implications for carbon budget calculations, for climate projections, and for the monitoring frameworks that underpin international climate policy. The scientific community is aware that this possibility is on the table, and the conversation about it is happening carefully and seriously in the kinds of venues that are not visible to the general public: departmental seminars, private scientific correspondence, the comment threads of preprint servers where specialists engage with each other in the technical language of their fields, the public-facing conversation, the one that eventually informs policy and public understanding, lags behind the specialist conversation, as it always does. This story, and others like it, are part of what closes that gap, imperfectly and incrementally, by bringing the specialist findings to the wider conversation before the policy implications are fully worked through, and before the official channels have decided what the appropriate public narrative should be. The ocean does not wait for the official narrative to be determined. It continues doing what it is doing, at depth, in the dark, whether or not anyone above the surface is paying attention. There is a pattern in the history of ocean science that this story fits into, and recognizing the pattern is the most important frame for understanding what the Central Pacific Acoustic Anomaly and everything that followed it actually means. The pattern is this: the ocean is consistently, repeatedly, and sometimes dramatically more complex, more dynamic, and more full of consequential surprises than our models and our intuitions suggest it should be. This is not a criticism of the scientists who built those models and developed those intuitions. They were working with the data available to them, and they built the best understanding they could with the tools they had. But the ocean is large and deep and old, and it has been doing things across geological timescales that leave only fragmentary records, and the window of systematic, instrument-based observation through which we view it is very short. The acoustic anomaly was there for at least 4 years before anyone found it, removed from the public data by an algorithm designed around the assumption that the deep Pacific abyssal plain was acoustically predictable. The venting field was there for an unknown but probably much longer period before the first AUV reached it. The thermal anomaly was there in the Argo data, visible in retrospect, not noticed because nobody was looking for it in that location with that expectation. The infrastructure of monitoring and analysis we have built for the ocean is genuinely impressive. It is also genuinely insufficient for the task of understanding a system of this size, this depth, and this complexity. And the insufficiency is not evenly distributed. We know more about the parts of the ocean that are easier to access, closer to shore, shallower, nearer to existing infrastructure. We know far less about the parts that are remote, deep, and far from the routes that ships travel and the places where cables run. The Central Pacific, by these criteria, is among the least well-monitored significant areas of the global ocean. It is remote from major research institutions. It is distant from shipping lanes and cable routes. Its depths are not associated with known economically valuable resources in the same way that continental margins or mid-ocean ridges are, and its apparent geological quiescence has made it a low priority for deep geophysical investigation. It is, in a word, overlooked. And the lesson of this story is that overlooked does not mean unremarkable. It means unexamined. The difference between those two things may be one of the most important distinctions in ocean science right now, at a moment when the ocean is absorbing more heat, more carbon, and more stress from human activity than at any point in the last several million years, and when the ways in which it responds to that stress are among the most consequential and least certain inputs into our projections of how the next century unfolds on this planet. We are operating a complex and increasingly pressured system with monitoring infrastructure that was not designed for the stresses now being applied to it, and we are finding out what that system is doing through FOIA requests and independent researchers and 18-month delays, rather than through a deliberate, well-resourced, comprehensive monitoring program that treats the deep ocean as a priority rather than a speciality. That is the structural problem that this story exposes, and it is a problem that persists regardless of what the full characterization of the Central Pacific venting field ultimately shows. The story of the classified data and the deep Pacific discovery is not a story about a monster or a government cover-up or an imminent catastrophe. It is more interesting than any of those things, and more consequential and more difficult to communicate without the dramatic shortcuts that those framings would provide. It is a story about the limits of what we know, about the gap between the monitoring infrastructure we have and the monitoring infrastructure we need, about the ways that institutional caution interacts with scientific transparency, and about the remarkable capacity of the deep ocean to be doing important things in places we were not looking with instruments we did not have trained in that direction. The acoustic signals in the Central Pacific are real. The thermal anomaly is real. The venting field is real. The methane in the water column is real. The classification request is real. The monitoring gap is real. And the pattern they collectively suggest of a deep ocean system that is more dynamically active in its methane cycle than existing models and monitoring frameworks assumed is real in the sense that it is supported by the available evidence, even if its full implications remain to be determined by more and better science. What is not real, what the evidence does not support, is any of the various dramatic overinterpretations that this story could attract. The venting field, even if it is large, is not evidence of an imminent methane catastrophe. The acoustic signals, even though they are unexplained, are not evidence of something non-scientific. The classification request, even though it is troubling, is not evidence of a conspiracy to deceive the public about something existential. What the evidence supports is the more sobering and more actionable conclusion that the deep ocean is under-monitored, that the under-monitoring has consequences, that those consequences are beginning to surface in ways that are scientifically significant and policy relevant, and that the appropriate response is not alarm but attention. sustained, well-resourced, scientifically rigorous attention to a system that has not received enough of it. Every number we use to describe the ocean, its average depth, its total volume, the proportion of the seafloor that has been mapped at high resolution, the estimated number of species living in its depths, the total carbon stored in its hydrate systems, comes with error bars that are wider than the equivalent numbers for the atmosphere or the land surface or the upper ocean. The deep ocean is our planet's largest and least understood environment, and the discoveries that emerge from it regularly revise those numbers in ways that shift our understanding of the whole system. The venting field in the Central Pacific is one of those revisions, one data point in a longer pattern of the ocean revealing itself to be larger and more complex, and more dynamically active than the previous data suggested. The acoustic signals that Elson identified, whose source remains formally uncharacterized, are another kind of revision, a reminder that the deep ocean's acoustic environment contains things that our reference libraries were not built to classify. Both of these findings, the known one and the unknown one, are invitations to look more carefully, with better instruments, at a system that has been operating largely below the level of our sustained attention for the entire history of human civilization. The ocean does not announce its significance. It does not generate headlines or press releases or social media posts. It circulates heat and carbon and chemistry through the largest connected body of water on the planet, at depths and on timescales that are difficult to observe and difficult to communicate, doing the work that makes this planet habitable without requesting acknowledgement for it. The least we can do is pay attention, and the most important way to pay attention is to build the monitoring systems, fund the expeditions, and support the researchers who are doing the work of looking into the darkness below 4,000 meters and telling us honestly what they find there. The document that was not supposed to exist has been read. The data that was filtered out of the public record has been analyzed. The expedition that was delayed by an unexplained interagency review has sailed and returned. The venting field that was not on any chart has been seen by an autonomous vehicle descending through the dark water above the abyssal plain of the Central Pacific. The methane in the water column above it has been measured. The scientific community has responded with the careful, serious, investment-warranting attention that credible and significant findings attract. And the monitoring gap that allowed all of this to go undetected for years, possibly decades, remains in place, unchanged by the discovery that exposed it, waiting for the next thing it was not designed to find. The ocean is not finished surprising us. The deep Pacific is not finished telling us what it contains. The acoustic signals are still there, recurring in their characteristic frequency range, produced by something in the dark below 4,000 meters that we do not yet fully understand. The venting field is still exhaling. The methane is still entering the water column. The Argo floats are still measuring the temperature of the water above it. The filtering algorithms are still removing signals they were not trained to recognize as significant from the public data stream. And somewhere in the unfiltered raw data of the global hydrophone network, in sections that have not yet been requested through FOIA and not yet analyzed by researchers with the patience and the context to know what they are looking at, there may be other doors, other signals, other patterns that do not match the reference library and that are being quietly removed from what the public is allowed to see, waiting for the next independent researcher who notices something odd in a public-facing chart and decides to pull the thread. The ocean is the planet's largest system and its least examined. What it contains, at depth, in the dark, in the places we have not yet looked with serious instruments, is not fully known. And that unknowing is not passive, it is consequential. The question is not whether there is more to find. There is always more to find. The question is whether we are building the systems, funding the expeditions, and paying the sustained attention that finding it requires. before the finding finds us first.